Hello, this is Jennifer Martinez, and welcome to the first section of linear algebra and its applications. What is linear algebra? It is the study of linear equations through vectors, which are a column of numbers, and matrices, which are a rectangular array of numbers. A linear equation in the variables x1 through xn is an equation that can be written in the following form, where b and these coefficients a1 through an are real numbers or complex numbers. You might recognize this equation from your past algebra courses. Ax plus by equals c. This is the equation of x and y, where a and b are the coefficients, the a1 and the a2. The c is this, like the b here, this constant on the other side of the equal sign. This is an equation, a linear equation, of two variables. And a system of linear equations, sometimes called a linear system, is a collection of one or more of these linear equations involving the same variable. So if we had another equation, we would have to use, say, x1 through xn. Systems of linear equations are at the heart of linear algebra, and we're going to use linear systems to introduce some of the main concepts of linear algebra. And we're going to show how linear systems are equivalent to vector equations and matrix equations. So let's start by looking at an example in two variable. Let's solve the equation, the system, x plus y equals 3, and then 3x plus 2y equals 8. If you remember from our algebra days, there are several methods for solving, but what I'm going to use here is elimination. To solve by elimination, what we want to do is multiply one equation by a specific number so that when you add them together, one of the variables will get eliminated. So what I'm going to do is I'm going to take the first equation and I'm going to multiply by -3 to eliminate the x. So if I multiply the first equation by -3, you can see when after you do that, when you add them together, the x's will be eliminated. Now you can eliminate the y just as easily. Let's go ahead and eliminate the x. So I'm going to multiply the first equation by 3. So you get -3x minus 3y equals -9. And then I'm going to leave the second equation alone. When I add those together, these two equations, you'll get -1y equals -1. Divide both sides by -1, and you would get y equals 1. You get a solution for y. Now you can plug this into one of the equations. I'll plug it into the first one to find the value of x. You can see the value of x is 2. So you have the ordered pair 2, 1. 2, 1 is called a solution to that system. There was other ways of solving as well. Substitution was one of them. The other one was graphing. Let's go ahead and try graphing. When you graph the first equation, you can see that the y-intercepts are just 3 and 3, aren't they? When x equals 0, y is 3. When y equals 0, x is 3. So I'm just going to plot, we'll call those 3, those 2 points, and draw a line. To graph the second equation, I don't feel like finding the intercepts. They don't look like they're perfect integers there. So I'm going to solve for y by subtracting 3x and dividing by 2. So we can see here that the slope-intercept form starts at 4. The y-intercept is 4 when x is 0. And the slope-intercept form tells me that I'm going to go down 3, 1, 2, 3, and over 2 to give me my second point. And that will give me my second line. So here's my first one. Here's my second. And you can see here that 2, 1 is a solution to both. It's the intersection. In general, a solution of a system is a list of ordered pair, we'll call them S1, S2, all the way to Sn, of numbers that makes each equation true when the values S1 and S through Sn are substituted in for X1 through Xn, respectively. And you can see in our case it is true, because if I plug in 2, 1, 2 for X and 1 for Y, 2 plus 1 is 3. And doing it for the second equation, 3x plus 2y equals 8, we get 3 times 2 plus 2 times 1 is indeed 8. So you can see each equation is true when you plug in the values 2, 1. In a linear system of two variables, how many solutions can you have? Do you always have one solution? Well, of course, two lines do not need to intersect at a single point. For instance, they could be parallel, or they can coincide, be the same line, and hence intersect at every point on the line. So figure 2 shows the graph that corresponds to these two different systems. And you can see here that in the first one, part A, they're going to be parallel. And the second one, part B, they're going to be the same. In the first one, there's no solution. And in the second one, part B, there's an infinite number of solutions. So those are the choices. A system of a linear equation, even in general, we will see, either has no solution, exactly one solution, or an infinitely many solutions. If we actually went and solved this by elimination, you can see here that it would make sense that there would be no solution, because if you add these together, you would just get 0 equals 2, and that doesn't even make sense. On this one, you can see it's the same line, because when you add these together, you would get 0 equals 0. On the first one, you would just write no solution. On the second one, you can actually say the solution is everything in the line. So if I solve for one of these, like say for x1, you can get 2x2 equals -1. So it's all the points that are on that line. By the way, x2, oops, that's supposed to be a -1. x2 can be anything. So sometimes they'll say x2 is free. So where it's x1 is equal to 2x2 minus 1, where x2 is free. So you can see when x2 is 1, the solution here would be 1, 1. When x2 is 2, x1 would be 4 minus 1, which is 3. So there would be many solutions. In fact, infinitely many solutions. Last concept here on this problem is a system of linear equations is called to be consistent if it either has one solution or infinitely many solutions. So this is called consistent because it does have many solutions. And the one above here was also considered consistent because it had one solution. So if it's consistent again, if it either has one solution or infinitely many solutions. A system is inconsistent if it has no solution. So this one right here was inconsistent. So let's look at another example. This is example 1 in the book. Solve the following system. Now we're going to go back to x1, x2s, x3s, though you could call it x, y, and z. And we notice that we have 3 equations here. I'm again going to use elimination, and I'm going to get rid of that 5x1 that's sitting over here. Notice how they're all aligned. There's a space, it means that there's the coefficient of the x1 term is 0 here. So I'm going to multiply the first equation by -5 and then add it to the third equation. Let me label these 1, 2, and 3. And let's go ahead and do that. So again, I'm taking -5 times equation 1, adding it to equation 3 to get my new equation. So -5 times equation 1 added to equation 3. So that would give me -5x1 plus 10x2 minus 5x3 equals 0. I'll just rewrite the second equation, or sorry, the third equation. Add those up. It's going to give me 10x2 minus 10x3 equals 10. And that's going to give me a new equation for equation 3. So I'm going to keep the first two equations, but for my third equation, I'm going to now write 10x2 minus 10x3 equals 10. And now I'm going to do it again. So this time I'm going to take equation 2 and 3 and get rid of or eliminate the x2's. So maybe I'm going to multiply the second equation by -5 and add it to the third. So let's go ahead and do that. So again, I'm going to take -5 times the second equation and then add it to the third equation to get -10x2 plus 40x3 equals -40. I'll just rewrite the third equation, add them together, and get 30x3 equals -30. We have it. We have a value for x3. But before I do that, let's go ahead and rewrite this into the new x3 again, or the equation 3. So this new line right here replaces equation 3. And again, yes, I know we didn't need to do that, but you're going to see why in a second. I'm now going to solve for x3, and I can see that x3 equals -1. And then what we can do is we can use back substitution to find the other values. So if I can plug in -1 into x3 in the second equation, you can see that x2 would be 0 because we would have here plus 8. So you subtract 8 from both sides, divide by 2, x2 would be 0. And finally, I can put both of those into the first equation to find x1. So here's the first equation, and I will put in a 0 in for x2 and a -1 for x3, and you can see x1 would be 1. And so we have the ordered triplet 1, 0, and -1. And here's the visual of that, the graph. The graph of each equation is now as 3 variables, so it's going to be a plane in the 3-dimensional space. So each of the original equation determines a plane in the 3-dimensional space, and the point 1, 0, -1 lies in all 3 planes. You can see it right there. It intersects all 3 of those planes and is a solution to all 3 of the equations. Now, if we did this with 4 variables, x1, x2, x3, and x4, this method of elimination would be very tedious. So we have to come up with a new method to solve these. And that's where we're going to introduce matrices. It says here that the essential information of a linear system can be recorded compactly in a rectangular array called a matrix that you can see here. So given the system, we have the same system as above, with the coefficients of each variable aligned in columns. So for instance, we have this 5, and then there's nothing here, so we're going to call this a 0, and 5 is going to be my first column. My second column is going to be -2, 2, and 0, and the last one, 1, -8, and -5. This is called the coefficient matrix, because it just has all the coefficients, or sometimes called the matrix of coefficients. And if we add the 0, 8, 10 here, sometimes I like to put a line there, but sometimes the book does not. It's called the augmented matrix when you add the 0, 8, and 10 to a fourth column. In the next video, we're going to show you how to solve the same system using this matrix instead of using the x1s and x2s and x3s. And it's going to save a little bit of time and a little bit of effort